Hello students, so in today's class we are going to learn the topic called equipotential surfaces. So now what is this equipotential surface? So if you see the name, as the name suggests, equipotential, that is basically equal potential on a particular surface. So a surface which has same potential at every single point is called as an equipotential surface. For example, this is a sheet of paper. At every point on this sheet of paper, the potential, let's say, is 5 volt. Then this surface or this sheet will be called as an equipotential surface. So let us look at this practically. Okay, so let's consider there is a charge Q. Okay, so since there is a charge Q over here, there will be electric field generated around this charge Q. Similarly, there will be certain potential which will be generated at each and every point around this charge Q. So I just select a specific point P. Let's say that this point P is my observation point. And I find that this point P has a potential, let's say V is equal to 5 volts. Okay. Let us also consider that this point P is at a distance of R from the source charge which is producing this potential. So will there be only one point which has 5 volt potential from this charge? Definitely not. There will be plenty of points which will have the same potential as 5 volt around this charge. So let's say one more point is over here, one more point is over here, one more point is over here. So how do we define this point now? Where this point will lie? So let us look at the formula for potential. So potential formula V is given by 1 upon 4 pi epsilon naught, considering this system is in vacuum, Q, that is the charge which is producing that potential, okay, divided by the distance at which we are finding that potential. This is the formula. Okay, so for this particular charge which we have kept constant, Q will remain constant. Okay, we want our V to remain constant, right? So this 1 upon 4 pi epsilon naught is already a constant, 9 into 10 raised to 9. So if Q is constant, 1 upon 4 pi epsilon naught is constant, we want our potential to remain constant. What should happen? Our R should also remain constant. So what can we say? That at equal distances from this charge Q, the potential is going to be same. That means that if we take distance R anywhere from this charge Q, distance R anywhere from this charge Q, what is going to happen? The potential at this point, every point around it is going to be same. That is 5 volt, 5 volt, 5 volt, 5 volt, and so on. Okay, so basically if we see this in a 2D, what will happen over here? If we try to join this point, this will look like a circle. This will look like a circle around this charge Q. But if we imagine it in 3D, what is it going to be? If this is the charge present in 3D, obviously at every point at the same distance, it is going to form a sphere. Okay, so that sphere on which the potential will be same, that surface is called as the equipotential surface. So we can consider a equipotential surface for a point charge to be a sphere. It will be a spherical surface. Okay, so for a point charge, equipotential surface is going to be sphere. And what is equipotential surface? A surface at which, okay, on which at every point the potential remains constant. So now there can be plenty of these equipotential surfaces, definitely, right? If I consider distance R1, around that particular charge, obviously the equipotential surface will be, let's say, this. Correct? Let's say this equipotential surface is a potential of 5 volt. This might have a potential of 8 volts because it is closer, right? V is inversely proportional to R. As we approach the charge, the potential will increase. Okay, R reduces, V will increase. Okay, so there can be plenty of the equipotential surfaces for a particular charge. So how the equipotential surfaces for a point charge will look like? It will look like something like this. So if I have a positive charge over here, this will be the equipotential surfaces, that is the concentric spheres. We'll have to draw the concentric spheres to represent the equipotential surfaces of that particular charge. So for the system of charges, for example, there is a positive charge and a negative charge in a system of charges. The equipotential surfaces will look something like this. If you see, they are close together in the region between the two charges over here. Okay, and this is the combination for a positive and a positive charge. So you will see the equipotential surfaces are far apart, okay, in the region between the two charges. This indicate a weak field in such region. There will be a weak field in this region. Okay, that's what it indicates. So you'll also see that the equipotential surface will also merge together. The equipotential surface of this charge and this charge can also merge together when it is a combination of positive charges. For a uniformly charged sheet, for example, if we have a uniformly charged sheet, for that equipotential surfaces will look something like this. So let's assume that there is some infinite plane sheet which is uniformly charged, which is producing an electric field, a uniform electric field E. So in that case, the equipotential surfaces will look something like this. They will be planes, okay, and the lines of force, okay, the lines of force, that is the electric field lines, are parallel and straight lines, and equipotential surfaces are equidistant parallel planes which are perpendicular to the lines of force. If you see, these planes will be perpendicular. If I draw the axis, they will be perpendicular to the line of force over here. Okay. Okay, so now let us look at the properties of our equipotential surfaces. So the first property we have is no work is done in moving a test charge over an equipotential surface. For example, if we have a charge and this is its equipotential surface, let's say this surface has a potential of 5 volt. That is, at every point on this surface, it's a sphere, okay? At every point on this sphere, the potential is assumed to be 5 volt. Okay, so supposing I take a test charge, let's say I keep a test charge Q0 over here, and I try to move that test charge from here to here, let's say. Okay, so according to this property, the work done in moving this test charge from this point to this point, let's say point A to point B, is equal to 0. Let's say work done in moving it from A to B is equal to 0. So why this is so? Why the work is being not done? Okay, so we have already seen, supposing this is my point A, I'm just redrawing it over here, and this is my point B, and I want to find out the work done in moving from A to B. Okay, this work done from A to B is given by the potential difference between the 2 points, let's say VAB, multiplied by the magnitude of the charge which you are moving. This we have already learnt, right? The work done in moving the charge from one point to another is nothing but the potential, okay, the potential difference between the 2 points multiplied by the magnitude of that charge. And what is the speciality of an equipotential surface we have studied? The speciality of the equipotential surface is that the potential at every point is same. So if the potential at every point is same, here it is 5 volt and here also it is 5 volt, what will be 5 minus 5? The potential difference between the 2 points? It will be 0. So VAB is going to be 0. Okay, and this term, entire term, will go to 0. That is why the work done in moving the test charge from A to B will be equal to 0. So now from this property we can learn a very interesting thing. For example, you have any conductor of arbitrary shape and you provide charges to this conductor. So what will happen to those charges? Those charges, if you are providing the positive charge, let's say, those positive charges which you are distributing to this conductor will get evenly spreaded over the entire surface of this conductor. This is the property of a conductor. When you give an excess charge to any conductor, what happens is it gets evenly distributed over the surface of the conductor until and unless you stop the supply. Once you stop the supply, equilibrium will be attained and the position of the charges will be fixed. Then they will not move. Okay, so why the charges does not move? Because all the points on this surface will come to the same potential. That is, the surface of this conductor will become an equipotential surface. Okay, and for the charge to move, for a positive charge to move, obviously it has to go from a higher potential to a lower potential. A positive charge moves from a higher potential to lower potential. So if the potential of this surface becomes same, obviously the charge is not going to move. Okay, practically if you think, just think of a metal block lying on the table. There is no supply to it, nothing is happening, nothing is connected to it. If you touch it, will you get a shock? No, you will not get an electric shock. Why? Because the charges are not in motion. Correct? What does that mean? If the charges are not in motion, that simply means that there is no current flowing in that metallic block, which is just idle lying on the table. Okay, so what is happening? The charges over there are in equilibrium position. They are not moving. And why they are not moving? Because it is just an equipotential surface. The potential at every point on that surface is same. Okay, and for charge to move, it requires potential difference. Unless and until there is a potential difference between 2 points, the charge will not move. The current will not flow in that particular body. So this is true for any kind of shape. Okay, if you have any kind of shape, when you give the charges to it, it will get evenly distributed over the entire surface of this arbitrary shape conductor, and this surface will become an equipotential surface and will be in the equilibrium state. Okay, so the next property we have here says the direction of the electric field is always perpendicular to the equipotential surface. So again, if we have this charge and this is our equipotential surface, okay, then electric field at every point on this equipotential surface has to be perpendicular. That is, theta has to be 90 degrees. This is my electric field, okay, vector. This electric field will always be perpendicular to the equipotential surface. So let's prove this now. Okay, so to prove this, we need to understand the relation between electric potential and electric field. So now let us consider 2 points on this equipotential surface. Let's say that this is point A and this is point B. Okay, so let's draw it over here. Let's say this is point A and this is point B. Okay, now for example, this at point A, the electric field is along the surface. Okay, it is not perpendicular. I'm not considering it perpendicular. Electric field I'm not considering perpendicular, but I'm considering it along the surface of the equipotential surface. That is something like this. Let's say this is my electric field. Okay, and I place a charge on this equipotential surface. Let's say this charge is Q0. So let's say it is a positive charge. Okay, so now if I put a positive charge in an electric field which is uniform, obviously electric field on this surface will be uniform because it is at the same distance. Correct. So charge is same, distance is same, so electric field at all the points on this surface is going to be same. Now if I place a positive charge in this electric field, what happens to the positive charge? Electric field is nothing but force per unit charge, right? So this charge is going to experience a Coulomb force, okay, and it will start moving in the direction of the electric field. So basically this charge is going to move in this direction. That is, let's say this is the direction of F over here. Okay, so now by moving, okay, this is going to move now, this charge from, let's consider this charge is moving from point A to B. So let us consider that the displacement is doing is ds, for instance. Okay, so it is going with a displacement of ds with a force of F. So obviously this is doing some work over here. This force is doing some work over here to move it from point A to B. So let us write down the equation for that work. Okay, so work done in moving that charge from A to B is nothing but it is the dot product of force and the displacement vector. This we know, right? Force into displacement vector. Now if I want to represent this force in terms of electric field, I know that force from this equation is nothing but the charge. So charge in this case I've taken is Q0 multiplied by the electric field dot ds. Okay, and in the previous lecture we have seen the work done in moving the charge is nothing but the charge multiplied by the potential difference between the 2 points. Let's say potential difference is AB. So if you see over here, there's Q0 on both the sides. So what would happen? This Q0 and Q0 will get cancelled on both the sides. So what do you see from here? The potential difference between the 2 points between AB, that is VB minus VA we can consider, is equal to E dot delta S. But what do we know about equipotential surface? On an equipotential surface between any two points, the potential difference is zero because the potential remains constant throughout the surface. So if you pick any two points on the equipotential surface, the difference between the two is obviously going to be zero. So VAB is going to be 0. And what is the expansion of this? E dot ds is nothing but E ds cos of theta. So if you look at the expression, our charge is moving, so displacement is not going to be 0. Electric field is present at every point around the charge, so electric field is also not going to be 0. So what can be 0 is cos of theta can be equal to 0. That simply means that this theta has to compulsorily be 90 degrees. Okay, so the electric field vector is always perpendicular to the equipotential surface. It will not have any component. So this is false. Okay, it will not have any component along the equipotential surface. So the next property we have is that equipotential surfaces never cross each other, just like the field lines. Okay, so if equipotential surfaces cross each other, what would happen? Okay, so for example, there is one charge over here. This one has an equipotential surface of its own, let's say Q1, and this is another charge Q2 which has equipotential surface over here. So according to this, these two equipotential surfaces will not cross each other. Because why? Because at this point of intersection, obviously there will be two values of potential, which is not possible. Okay, so one point can have only one value of potential. So that is why we say equipotential surfaces can never cross each other. Now you may ask, supposing 5 volt equipotential surface of this and 5 volt equipotential surface of this come at one point, will they intersect? The answer is no. Even if it is 5 volt for this and 5 volt for this, they will not intersect. They will just merge with each other, just the case as we saw over here. Okay, so at this point, if you see, this is not intersecting, they are just merging with each other. Why are they not intersecting? For example, there are two surfaces like this. Okay, there are two equipotential surfaces like this. At this point of intersection, what do we know about electric field? The electric field is always perpendicular to the equipotential surface. For this surface, for this particular surface, the equipotential surface, the electric field is going to be something like this, let's say E. Okay, and for this surface, it will be 90 degrees at this point, like this. So it will be 90 degrees to this surface, and this one's electric field will be 90 degrees to this surface. And is this possible? At a single point, is it possible to have two different directions of electric field? It is not possible. That is why even if this equipotential surface is having a potential of 5 volt and this equipotential surface has same potential of 5 volt, they will not cross each other. They will just merge like this. Okay. So this was the last property of equipotential surface. So this is it about the equipotential surfaces. In the next class, we will learn a new derivation which will be giving us the relation between electric field and potential, which we just briefed about. Okay, in today's class, we'll be seeing it in detail. Thank you.